Hello everyone, I'm Professor Muthana. In this lecture we're going to go through a one-dimensional wall and I'll go through a one-dimensional wall that's in parallel. So if we start with an example of two composite wall that are placed in parallel, this is material A and that's material B. Each material has its own thermal conductivity. Heat is being transferred from the left side to the right side. This point here is considered T1. It's isothermal throughout the wall, meaning that the temperature is the same. This temperature here is T2. Heat is flowing into the wall, and then it's being broken down into different Qs. This is QA, that's QB, meaning that the heat entering into material B. Back here, that's the total heat transfer. Same thing here. That's your total heat transfer. This is QA and that's QB. Okay. The length of the material is L, which equals to LA and LB. The area is different. Each shape has a different area, but the length is the same for both. So to start solving this example here, step number one is to convert the schematic we have here into a thermal circuit. So let's draw that out. So the first knot is T1. T1 is broken down. Let me draw this better. T1 is being broken down into two paths. One goes through resistance of A, R conduction A. For now, we're disregarding the convection that's happening here on both sides of the wall. We'll go through that later. But to continue on, the second material has a resistance of R conduction B. And then they join parts here at knot T2. And heat is flowing out. So we're required to find the heat flow or heat transfer Q. Okay? We know that Q equals change in temperature divided by the total resistance. Change in temperature is T1 minus T2. Now the resistance in parallel is different than resistance in series. So it will be R conduction A times R conduction B divided by the sum of the resistance in parallel. And that's the resistance for a parallel situation. Okay, now Q is your total Q, as we mentioned here. In order to find QA and QB, how much heat is being transferred in material A and how much heat is being transferred through material B, you'll say QA equals total Q times resistance of conduction of material B divided by sum of the resistance in parallel. Okay, and now that you solved for QA, we know that Q equals QA plus QB. Therefore, QB equals total heat transfer minus QA. You can use this equation, or you can solve for it the longer way, which is QB equals Q times resistance on material A divided by the sum of resistance in parallel. Either method is correct. Okay, notice how when we're solving for the heat transfer, the heat flow for A, we're using the resistance of material B, and when we're solving for the heat flow of material B, we're using the resistance of material A. So keep that in mind when solving a problem. Okay, now we're going to do the same example, but what we'll do this time differently is we're going to introduce conduction to both sides, which makes sense because both sides are exposed to air. So we'll do the second example. Same composite wall with two materials in parallel. That's material A, material B. Each material has its own thermal conductivity. And the only difference this time is that there is convection in both sides. The surrounding temperature on the left is T infinity 1. Surrounding temperature on the right is T infinity 2. We also have a convection coefficient on both sides. Okay, heat is flowing from left to right. Let me redraw this. Okay, this section here is our first knot, T1, T2, and again T infinity 2 and T infinity 1. Also, one thing I forgot to mention is that we're going to assume that this section here is adiabatic, meaning that there is no temperature flowing from B to A or from A to B. We're also assuming that these nodes here are isothermal, meaning that the temperature T1 is the same at any point in this surface, and the temperature of T2 is the same at any point in this surface here. Now, the difference will show up when drawing a thermal circuit. So, we'll start with T infinity 1. When heat transfers, it goes through a convection resistance 1, R convection 1, before it reaches T1. When it reaches T1, the heat is split into two. One goes through material A, runs through a resistance of conduction A. The second path goes through material B, which runs through resistance of conduction B. They're joined again at node 2, which is T2. Then it goes through convection again, which is R convection 2, before it reaches T infinity 2. Okay? So after we drew the thermal circuit, now we can start solving for Q. Q equals change in temperature divided by resistance, total resistance. Change in temperature is T infinity 1 and T infinity 2. Therefore, T infinity 1 minus T infinity 2 divided by the total resistance, which in this case we're working with a parallel circuit and 2 in series. So it's a series and parallel system. Therefore, we'll add the we'll write down first the parallel section of it, which is R conduction A times R conduction B divided by the summation of R conduction A plus R conduction B. So that hasn't changed from the previous example. The only thing that changed is the 2 convection resistance in series. Therefore, we'll add them to the total resistance, which will look like this: R convection 1 plus the resistance in parallel plus the second resistance in convection in series. And that's how you'll get your total heat transfer for a system of mixed with a series and parallel composite walls. Okay. QA and QB won't be that different. Will be the same actually as we solved before, which is R conduction B divided by R conduction A plus R conduction B. And the reason it hasn't changed is because QA and QB are in parallel. Therefore, it's the same way solving them. The only thing that were added was 2 convection nodes, which was T infinity 1 and T infinity 2. Okay. QB will be the same, which is Q minus QA. Okay. You won't be seeing like the maximum combinations you'll see is series and parallel, but other than that, everything will stay the same. It could be different in the orders, but you won't get anything more complicated than this here, as 2 series and a parallel. That's it for this video, and see you in the next class.